This topic is topic 9, motion in fields. It will take 8 hours. First, we'll look at 9.1, projectile motion, which will take 2 hours. State the independence of the vertical and the horizontal components of velocity for a projectile in a uniform field. We know that the horizontal component of velocity is going to be constant in equal lengths of time. It will travel an equal distance horizontally. Vertically, there will be acceleration due to a gravitational field. It does not matter what the vertical component is, the horizontal component will always be constant. So basically, when you do any problems, you have to treat the horizontal component and the vertical component separately. Describe and sketch the trajectory of projectile motion as parabolic in the absence of air resistance. A parabola is a function that in its simplest form has this form: y is equal to x squared. And this is a parabola. You've seen these in maths. Y is equal to x squared. You could try it on your calculator, and this is a pattern that you will get. A projectile motion will have the same shape, but it's basically inverted, like this. So this is the same as how the position changes with respect to time for projectile motion. And you can see that y is equal to x squared resembles this. Basically, s is equal to ut plus half at squared. This is the part that renders it a parabola. So y is the horizontal axis, the x-axis a measurement of time. Well, as we've said already, that the horizontal component is constant in terms of velocity, because we know that horizontally it's distance, but this is a measurement of time. Now, when we have air resistance, the air resistance is proportional to v squared. Therefore, the horizontal and vertical distance travelled is less in the presence of air due to the air resistance. So then that will not be quite a parabola, but we need to be able to sketch what it looks like. Describe qualitatively, which means describing the shape of air and the effect of air resistance on the trajectory of a projectile. This is a projectile with no air resistance. Then we have to draw a projectile where there is some resistance, and it will look something like this. There are three main factors to look for here. The most obvious one is that the maximum height is not going to be so high. It loses a lot of energy at the start of the trajectory because it's going so quickly. So it will lose that energy and the path will be under that of the trajectory without air resistance. So the first point is that maximum height is not so high. Secondly, because it loses horizontal velocity, it will actually be steeper towards the end. So it has a steeper trajectory here than here. And then there's another point which you can't see so well from this graph, from this sketch, is that from the start the projectile with air resistance will lag behind that without air resistance. So it will lose energy, and this is why it will not go so high. The range will not be as far, and it will be steeper at the end. Solving problems using the suvat equations and the conversion of energies. Okay, a cannon fires a cannonball at 60 degrees to the horizontal from a 20-meter sea cliff top with a speed of 100 meters a second. How do we look at this? First, when you solve this, you must resolve the velocity into horizontal and vertical components, and then you treat them separately, treat them independently. So, a question: how high does it reach? Well, you basically have to take the vertical component only. Find out the vertical component of 100 meters a second in the vertical direction, given that it's fired at 60 degrees to the horizontal. Then you can use the suvat equations to find out what the distance will be. Remember to be consistent with the direction of distance or displacement and the direction of acceleration. Find the time taken to hit the sea. In other words, when is it level with the bottom of the cliff? Here again, I would recommend you take the vertical component, find the time it takes to go to the top, and then do it in a second stage, the time it takes to go from the top to the bottom and hit the sea. Or you could do it in one step. However, you will end up with a quadratic equation. If you're happy in doing that, then you're welcome to it. Find the range. How far in the sea, how far out to sea from the cliff does the cannonball land? So here you use the time that you calculated in this question, and you find the horizontal component, which you know is going to be a constant, and it's easy. Distance is equal to speed times time, or velocity times time. And last, calculate the kinetic energy, and hence the velocity, when it hits the water. So in this question, you only need to consider changes in potential energy and kinetic energy. I want you to try to do this problem now. Your answers will be submitted in the reading quiz at the end. There will be 4 questions, and so you need to work on this now and try to submit your answers, and then I will have an idea how well you've managed to do this by your answers.